in this talk, I'm presenting a new work in 3 directions: creating multilingual sense embeddings, performing state-of-the-art word-sense disambiguation, and state-of-the-art semantic role labeling, and as much as possible scaling multilingually. This is joint work with several colleagues and students of mine, without whom this would have been impossible: Bianca Scarlini, Michele Bevilacqua, Andrea Di Fabio, Tommaso Pasini, Simone Conia. Let me start with a real need, a real word need. So you have, we all use machine translation systems. So if I ask a state-of-the-art machine translation system, and this is an old example that still has this issue, and there are many: is it healthy to drink from a copper vessel? And I translate this into Italian. Vessel is an ambiguous word. So I get, is it healthy to drink from a copper ship? So obviously this is not what you mean, and common sense would tell you that, at least. Even if you know that this word is ambiguous, you wouldn't translate vessel into rame, because, sorry, nave into ship, because obviously that's it doesn't make sense in this context. And so even though current systems take a context into account in a very deep way, they still fail at understanding what's written in a text. And so this is the one of the objectives, the key objectives of natural language understanding, and also of my team at Sapienza University of Rome. So I'll talk about 2 of the 3 main tasks in natural language understanding at the semantic level. So word sense disambiguation is the base task, where you have to associate meanings with words which occur in context. Let me reduce this, okay. So you have a sentence like: the employer fired the programmers from the software company, and you would like the system to associate concepts with words that occur in context. Like, for example, here, fire is ambiguous, and you would like to the system to choose the right meaning of fire. Semantic role labeling is the second complex task in NLU, and here you want to identify the key verbs or predicates, could be also nominal predicates, that identify, that denote that drive the meaning of a sentence, and then label the arguments of this predicate with the right argument roles. This is, for example, the output of a system, quite well-known system, and unfortunately fire is wrongly disambiguated. So you see the connection between these 2 tasks, because firing here, you don't fire at programmers to fire them. So unfortunately, again, systems don't seem to understand very well, at least in a few examples. And finally, the third task is semantic parsing, in which you try to produce a graph representation, a structured representation of the sentence by connecting the various parts, the various meanings that are denoted by words or phrases in the sentence. But this is outside the scope of this presentation. So the key goal in my lab and in general in NLU is multilingual machine reading. So you would like machines to potentially read the entire web and understand, at the semantic level at least, what's written there. And so as a result, you would be able to answer all kinds of questions, summarize, translate in all languages. And to do this, you have to tackle one of the most important and difficult problems in natural language, which is ambiguity. And so you have to overcome these complexities of natural language. Now let's go back to word sense disambiguation. Let's start from this first task. Let's look at this sentence: the mouse is eating the cheese. We would like a system to identify the right meaning of mouse, also of eating, because that's also an ambiguous word, and provide an explanation for these words used in a given context. Now, there are 2 main directions in word sense disambiguation today. Obviously, we all use supervised approaches, and in the last few years, we've been using neural deep approaches that provide one or more neural architectures, combine one or more neural architectures, and as a result can, thanks to taking a whole word sequence into account, can learn from context and normally get very high performance, as we'll see later during the presentation. However, the minus of this approach is the lack of annotated data. So you need quite large training data in order to inform a neural architecture. And this is also called in lexical semantics the knowledge acquisition bottleneck. So coverage is the biggest issue here. While the other approach that tackles these issues in supervised approaches in word-sense disambiguation is a quite special approach that is called knowledge-based. So rather than learning a supervised model that performs a disambiguation task, these approaches exploit the structure, the general purpose structure of some lexical semantic knowledge resource like WordNet, BabbleNet, and others. And this allows to scale across languages because the coverage that these resources provide is quite high, and also is independent of there's no focus on a given domain, because these are general purpose resources like encyclopedias, dictionaries, and so on. And also thanks to the integration of different resources and different languages, you can scale to arbitrary languages, even those for which you wouldn't have any training data at all. And this is also thanks to multilingual synthets that are available in BabbleNet, for example. So sets of synonyms that include lexicalizations from many different languages. So a single concept is lexicalized in many languages. The minus is that normally these approaches have lower performances because they fail at taking the keywords, the context into account, which is what is best done by supervised approaches. And so a key proposal of this talk, of the work that I'm presenting, but also other works in the literature, is to integrate these two approaches to get the best from these two words. In terms of supervised word-sense disambiguation, where the system has to be trained to then tag the words, the content words like nouns, verbs, adjectives, and adverbs with the most appropriate meaning from a sense inventory. We have two main training corpora for the task. One is SEMCOR, which is a historical corpus of more than 200,000 words annotated with senses from WordNet. And another one, which is more recent and recently has been very popular in the literature, is the WordNet tagged glosses, the WordNet tagged gloss corpus. This corpus includes many more annotations. Most of them are gold annotations, that is, they are manual, and others are obtained automatically with very high precision heuristics. These two corpora, however, are only in English, so this is English text, and there's no big corpus in other languages. And so this is what motivates an approach that tries to integrate information from knowledge bases, lexical semantic knowledge bases. And so we want to overcome the language barriers. And a solution that we put forward is to move from an approach in which you try to model words. And now this is a picture which might look old-fashioned today because we're all working with contextualized word embeddings. And so word embeddings, like non-contextual word embeddings, are now a bit out of fashion. But still, you will understand that having a representation for an individual word cannot be very helpful to scale across languages, while having representations that take sense into account and provide a vector representation for one sense of the word and another sense of the word, like here you have the financial meaning and the riverbank meaning of the word bank, will help a word sense disambiguation system discriminate between the various meanings of that word. And now we'll see that we also take advantage of contextualized word embeddings to do that. So the solution that we put forward is to move from the lexical to the semantic level. And so link vectors to meanings that are available in a meaning inventory like BabbleNet or WordNet. And the first work that I would like to present is SenseEmbed, which is a work that we presented at AAAI this year about how to create sense representations starting from contextualized embeddings like those produced by BERT. And obviously this could also apply to other transformer-based architectures. So we can create sense embeddings starting from contextualized embeddings in 4 steps. First, we focus on a given concept. So this is a concept that can come, as I said, from WordNet, from BubbleNet, which is a superset of WordNet. So you have a concept in mind, you have a concept, a focus concept, and you want to retrieve Wikipedia articles that are related to this concept and the set of sentences that contain words related to this concept. So we create a lexical profile based on a measure called lexical specificity from the page or the lexical information, the text that is associated with this concept. And as a result, we have a ranking of relevant words for the concept, and we retrieve sentences from related pages that contain those words. Now we create a word embedding for each of these words. But we create a word embedding as an average of contextualized embeddings from BERT, of the context of the word in context in the various sentences in which it occurs. Like, for example, here you have device, and that's a word that is related to mouse. And so we take all the occurrences of device and we create a word embedding as an average of the contextualized word embeddings therein. And then we can create a synset embedding by by calculating a weighted average of these related word embeddings. And so as a result of this, we get a single vector representation for a synset. Like here we have mouse and computer mouse. We average all the representations of the word embeddings, the contextualized word embeddings of these words, and we create a representation of the context in which mouse tends to occur. And then we pair this, we concatenate this representation with the representation of the definition of the gloss of the concept. So here we exploit BubbleNet. So we take the definition of the concept. We take the synonym. We prefix the synonyms in the synset, and we also prefix the sense, the word we are specifically interested in, so that we can create sense-specific embeddings. So an embedding for mouse, an embedding for computer mouse. For example, if I had car, motor car, and automobile, I would prepend different words at the beginning so that I would create slightly different sense embeddings. As a result, so we create a BERT representation of the definition by averaging the various contextualized embeddings of the content words, and we concatenate these two representations and create an embedding of the concept. And then we do something very, very simple. We use one nearest neighbor to choose the meaning of a new target word in context. So now that I have an embedding for mouse as a computer device and an embedding for the animal meaning of mouse, now I have a sentence, the mouse is eating the cheese, and I'm interested in disambiguating mouse. I just see how distant this vector representation from BERT is from the two sense embeddings, or let's say contextualized sense embeddings of the two meanings of mouse. This looks very simple, but results are surprisingly high. So here you can see we are comparing against the knowledge-based approaches, purely knowledge-based approaches that don't exploit supervised models, against traditional supervised approaches which employ either SVM plus word embeddings or BiLSTMs, or more recent approaches, but still LSTM based. Then we also compare with approaches that exploit transformer based or contextualized word embeddings, and also approaches that integrate some knowledge. And we see that if we take the version that I described in this in the past few minutes, you see that you achieve close to the state of the art. Let's say if we exclude for a moment this system here, you achieve overall above the state of the art. So by concatenating the 5 data sets that are normally used in word sense disambiguation from SEMEVAL and SenseVal competitions, you achieve the state of the art with some varying performance individually by data set. This is another approach that integrates knowledge, and so, but is also supervised, while Sense and BERT is not strictly supervised in the sense it's not trained. well, obviously it benefits from BERT and so on, but here instead we are exploiting SEMcore in LMMS to create the vectors, which is what we are also doing here. In this new version, Sense and BERT SUP, we are also taking advantage of SEMcore to create an average of the sense-based word occurrences and improve the representation of the sense embedding. And obviously these are sense annotated occurrences, and this makes the task supervised. So now if we integrate knowledge and the supervision from the training data to create again a contextualized embedding, a better contextualized embedding, and use 1NN to choose the right meaning, we beat the current state of the art and achieve beyond 80% performance across the board. So this is a fantastic result, considering that this is just vectors that we are comparing based on their distance or their cosine similarity. However, this is only for nouns, because Sense and BERT is based on information that normally comes from Wikipedia, and Wikipedia tends to encode pages that concern nouns or names, but not verbs and adjectives and adverbs, which we would also like to disambiguate. However, this result is effective and interesting. We can also scale multilingually, because if we use multilingual BERT, we can create multilingual embeddings which are compatible across languages. And this is also thanks to using BabelNet concepts and senses. And if we do that, we beat the state of the art, and interestingly, there's not much supervision you can exploit in non-English languages, because, as I said, there's no non-English sense annotated corpus on a large scale. So these are all approaches that exploit silver data that has been created automatically, while Sense and BERT just exploits the knowledge from the knowledge base plus BERT. And now, so this is a first approach. Now, what if we wanted to go fully neural? So there are recent approaches that exploit neural architectures to perform the word sense disambiguation task. We have SEMcore, we have the WordNet tag glosses, and we can inform by LSTMs, or more recently transformer-based architectures, to train our system to output the best possible meaning of a word in context. However, these approaches suffer from unseen senses during the training, because if I have never seen the label for a given word or for a given sense of a word, it will be hard, even for very powerful systems like BERT, to output the right meaning for that word in context. And so recent improvements presented at last year at key conferences in NLP show that if you integrate some knowledge from WordNet, like the glosses from WordNet, which includes the definitions. I see I have a question. I'll stop in a second. If we use some knowledge from WordNet, again, as I said, in the sense of glosses, definitions, and we, for example, predict whether a gloss is pertains to a certain word in context, or we map words in context to the space of the gloss embeddings. So we have the definitions represented in a certain vector space, and we map our context vector, our contextualized word embedding onto this space, and then we compare. So these approaches get improvements, and so we can further improve the performance of these systems by integrating textual definitions from WordNet. Let me see the question, so if I can immediately answer this. Yeah, so that's a good question. I see Martin is asking it. So what are the reasons for the differences in the results between the different sensible data sets and semi-eval data sets? Let me go back to this slide. I like this interactive way of asking questions. So yeah, so you can see that some tasks are harder and in general, like for example, if you take this column, this SemEvolve 2007 column, this is generally harder than other data sets. However, you can also see that when you use that, the SemEvolve data sets are normally, in a sense, easier than the SemEvolve data sets. And this is, at least if we use traditional approaches. And why do I say traditional approaches? Because when these data sets, these new data sets were created, some of them we created ourselves because we organized the tasks. We took care of differentiating as much as possible the domains of the text. So here you have a wider coverage of domains, which in a sense creates more problems for systems that don't exploit any knowledge or don't have sufficiently wide training data. So this is one of the reasons why you have varying performances across datasets, and also these datasets are relatively small. So we're talking about 1,000, 2,000 items per dataset to be disambiguated, and that's why I think that the all column is the most interesting one, because it takes, like, it merges, it concatenates all these data sets, and it is in the order of several thousands of items. So I hope this answers your question. Now, we said that we can improve traditional supervised approaches by integrating some textual definitions into the architecture. However, these approaches don't leverage the structural information that is available in resources like WordNet or BabbleNet. WordNet is a graph. It's not only a computational lexicon and based on psycholinguistic principles, and the organization of concepts is by synsets, so sets of synonyms. So you have definitions for the concepts that we also call glosses, but you also have semantic relations that connect pairs of meanings. So here you see that car is a motor vehicle, that car is part accelerator. So why not exploiting this information and integrating it into the neural architecture? And also, why not exploiting the effective sense embeddings that one can create from approaches like Sense and BERT? And so this takes us to very recent approaches in neural word-set disambiguation that exploit so-called structured knowledge. So rather than just using knowledge from WordNet or other resources, we try to make use of semantic relations, of relational information. And so there's a recent paper last year from Kumar and colleague, which uses these relations in the loss function to train the definition encoder. So the definition is learned based on exploiting also in the loss semantic relations. However, the relational information is only stored implicitly in the parameters after the training is performed. Vial et al. Also last year used relations to conflate senses, because we know that WordNet, for example, is a very fine-grained resource. And so we would like to reduce this fine granularity by creating coarser senses and conflating them based on relations like mostly hypernymy, generalization, hyponymy, specialization, and we could also use meronymy, part of, and so on. So here, this is also interesting because it reduces the granularity. However, some information that is specific to a given synset, that maybe is a specialization of another synset, of another concept, but contains additional information that is useful for the disambiguation task, this is lost. And so at ACL, in a couple of weeks, we are presenting a new work that I'm anticipating here, which is called eWiser, for enhanced word-set disambiguation integrating synset embeddings and relations. And here we are doing two things. We are proposing to inject semantic knowledge from WordNet and BabbleNet, both implicitly and explicitly. So implicit knowledge comes from the integration of synset embeddings. So we take latent representations of synset embeddings, like those that we created with sense and BERT, but we also use LMMS, which comes from last year, and explicit knowledge. And this is done through the incorporation of a WordNet-based adjacency matrix within the neural architecture, so that we can exploit this structural information explicitly within the network. And this is added on top of a baseline, but still complex because it's BERT-based neural classifier. So in brief, we start from BERT largest hidden states for the last 4 layers. And so this is pre-computed. So we start from the last 4 layers, and then we use a very simple 2-layer feed-forward classifier. You should never copy from a PDF. And we just add on the use of different activation function, like the swish function. And what we do is, so we exploit the sense embeddings by introducing a matrix that contains the implicit knowledge and that is initialized with the sense embeddings coming from any of the approaches. So this goes from all the possible meanings of the of available in a given resource, and that should be output by the system, to the number of dimensions that you have in a sense embedding. And then you also have an additional term, an additional computation, which is the explicit knowledge. So you have the adjacency matrix that is, as I said, contains the WordNet graph edge information, and this is multiplied by the output of the previous computation with the sense embeddings, of the output of our architecture with the sense embeddings, and then this is also compared, multiplied by the adjacency matrix, while at the same time preserving also the information and summing the previous matrix to the result. This is a batch-based computation. That's why we have matrices. And finally, then we apply softmax, and we choose the most appropriate meaning of a word in context by choosing from the those meanings, those synthets that are sense that contain that word as a sense. Obviously, we don't choose among all the possible meanings that are at the output layer. And let's look at an example so that we better understand how it works. So we have a sentence. We have a word in context, root. The root of 4 is 2. Then we apply BERT, and we get a contextualized representation of the word in context. We input this to the feed-forward that computes the logits of our possible senses. And as a result of this, we can compute a score for each possible sense of root, actually for each possible sense in WordNet or in BabbleNet if you wanted to extend it to BabbleNet. So as a result of this relatively simple architecture, because it's BERT plus 2 plus feed-forward, we have a score for each sense available in WordNet. And this includes senses of the target word. So we have a score for the different senses of root. And as you can see here, the highest scoring, and this is a real example, the highest scoring sense of root is the solution meaning, which is okay, but that's a solution of an equation. So the other meaning that would be ideal is the squared root meaning. And so if we had to choose here, we would make a mistake. Now, what we do is to consider the logits, the scores of the related senses, of the senses that are related by a semantic relation to the various meanings of the target word. And so, for example, for botany, we consider plant organ, root as a verb, rootlet, and for root, we consider number, and so on. And we multiply their scores times the relevance of those edges to the sense of interest. And so we give an importance to these scores. So we multiply these by the score, and then we sum this information to the initial logit. And so this is what we call the structured logits. So we create logits that are obtained by exploiting structural information from WordNet and potentially any other lexical knowledge base that has a graph structure. As a result of this, in this example, but in general, we obtain higher performance, higher scores before the softmax for the sense that is most relevant and to which other meanings, other senses contributed, so that the final score is highest, and in general, scores of other senses that are irrelevant are lower. And so this is the objective of structured logits. So in the experimental setup, we do something similar to what we did earlier. So in the test, we use the all data set, that is the concatenation of all the English data sets in the framework of Raganato et al., which includes the 5 sensible and semi-eval gold standard data sets for word sense disambiguation. We use one of the data sets as development, which is quite common, and that's the normal data that is used. But obviously, we also have performance when we exclude this as a test set. And as training, we use the 2 data sets that are normally used in word sense disambiguation SAMCore and the WordNet tag glosses plus examples from the glosses. We also test on multilingual data sets, which are the non-English counterparts in 4 other languages from the semi-eval 2013 and 15 tasks, WSD tasks. These are the results, and we compare the results against the best performing systems. As I said, LMMS is based on a sense embedding representation that is also informed by training data. Glossbert is also supervised. And so all these approaches are also leveraging information from WordNet or other, mostly from WordNet, I would say. And we also differentiate, in the case of Vial and Weiser, between the use of WordNet tag glosses when they are tagged indeed. So you have a definition, a gloss, and some of the words in the gloss have been tagged with the right sense, manually or semi-automatically, as I said, with high precision. And this is the tag, with tagged glosses, which is the highest performance option. A lower performance option is one in which you don't use the labels manually or automatically associated with words that occur in a definition of a meaning, but you just exploit the definition, the unannotated definition, but you add the word being defined and you tag it with the right meaning, because you know that this definition is for a given sense of the target word. So you can create a corpus of untagged glosses in which there is one tag per gloss, which is the word being defined. So you have, I don't know, root, and then you have, oops, sorry. And then you have here the definition, the number, blah, 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 blah. And so this is tagged. So you can create automatically a tagged corpus that doesn't exploit the manual annotations here. And this is the without tagged glosses. So you still exploit the glosses, but you don't exploit the tags, but you use the tags from the word being defined. And this gives you a drop in performance of about a bit more than around 2 points. And as you can see, exploiting the initialization from sense embeddings plus the structured logits gives you a considerable boost in performance and gives you more than 80% on the entire data set, on the entire concatenation of the data sets, which has never been achieved, and which is a psychological plateau based on calculations for interannotator agreement for WordNet, even though we have some concerns there, but we can talk about it later if you want. So this means that integrating knowledge into a neural approach in the best possible way can considerably improve the performance of a system trained on standard annotated data. And finally, if we scale to other languages, we start from the baseline classifier where we don't integrate knowledge. This already beats the previous state of the art because, you know, the power of BERT and the contextualized representations is considerable. But if you then integrate the structured logics and the sense embedding initialization, you get further boost in 3 out of 4 languages. Probably German requires a bit more attention based on its morphological complexity. But generally, you can see that performance grows considerably. And if we compare it with the previous state of the art, going multilingual with this approach and exploiting BabelNet, considering that this model is trained only on English data, so there's no training data in non-English languages, while we exploit the structural information from WordNet and BabelNet, gives considerable boost in performance, which is very interesting. I'll stop here to see if there is any question, because now I'm moving to semantic role labeling, which, as I said, is a second key task in NLU. Let me see if there is any question. I don't see any. So maybe let's see later. Okay. Okay, now I'm moving to the semantic role labeling task. In this sense, these 2 tasks are very interrelated because, as I said, if I have to choose, so in this task I have to say who did what to whom and sometimes where and so on. And so I have to first identify the predicate or the predicates, and and then I have to identify the arguments. And then I have to disambiguate this predicate to choose the right meaning of this predicate. And based on this, I have to label the relationship, the predicate argument relationship between that predicate and the various arguments that were identified. So this is a lot more semantics, even though there's a disambiguation task going on, because I have to choose the right meaning of this predicate in order to choose the best roles and role labels for the arguments. And what is around? We have a lot of interesting resources, very rich. This is not against these resources, but there are issues. And so when there are important resources, one has to see whether these resources create, I don't know, inherently create barriers or anyway need to be improved to improve the task. And so if we consider, so the resources are FrameNet, VerbNet, and PropBank. If we consider FrameNet and VerbNet, these 2 have quite incomplete coverage. So they're fantastic resources, but they don't cover the whole lexicon, not even the whole lexicon of verbs. And so if I wanted to use these as sense inventories for the predicates, I would fail at disambiguating the senses of some predicates. And this is what makes WordNet quite powerful and interesting, because it has full coverage or almost full coverage of English. Then if I consider FrameNet and PropBank, here an issue is that their semantics is predicate specific for the roles. So when I say a given predicate, like, I don't know, eat, has argument 0, argument 1, argument 2, these numbers, arg0, arg1, arg2, are specific to this predicate. And so this makes it harder to scale across predicates and across frames, okay? If we consider VerbNet and PropBank, they are missing verb class semantics. So semantic information that aggregates predicates. So there's no aggregation of different predicates to say this is a frame, which is instead what is done in FrameNet, for example. And so to bring together a number of predicates and say that they make up the semantics of a given semantic scenario. And altogether, they are all tied to specific languages, which is mostly English, even though there are versions of PropBank and FrameNet in other languages. I don't know about VerbNet, but the point is that most of the time they are not interlinked. And if they are interlinked, there's no unified semantics. So this creates a barrier to scale multilingually. There was a question, so let me look at the question. Oh, yeah, that's a good question. The question is that for disambiguation, we're using languages that are Neo-Latin languages. So, and German shares the same root with English. So I agree. So basically, we are testing here two main kinds of languages. It would be great to test on, I don't know, Chinese or Arabic. We don't have gold standard data sets for this. However, I can anticipate that we are organizing a seminal task this year on multilingual wording context, which is a new task that came out recently in quite simple, but still interesting, because you have two, you have two sentences and the same word in context, and you have to say, the system has to say whether these are used in the same sense or not. And currently this wording context data set is available only for English. And we propose a task that is going to be organized, and the data will be out in early September, in which we have data in the six United Nations languages, which is great because many of these languages are from different families. So you have Chinese, you have Arabic, you have Russian, you also have Spanish, French, and English, which makes the full set quite varied. Same for semantic role labeling. We're also organizing a multilingual semantic role labeling seminal task this year, where you will have the same six languages, and this will enable comparison against word languages at scale. So I'm sorry I cannot provide results for other languages now, but there are no gold standards available. There will be very soon. Thanks. Okay, so now how to address these issues? Again, we're talking about semantic role labeling. What we did was to do some manual work, because sometimes you need to do manual work in order to enable automatic systems. And so we created a new resource that addresses all of these issues. And to create this new resource, we started from WordNet. And the reason why we did that was that WordNet is included in BabbleNet. And so it makes it very easy, once you create a semantic resource from WordNet, to then scale to any other language. And even if you say, I can hear you, you could say, yeah, but you see, BabbleNet doesn't always cover all those languages, or at least provides high coverage only in a few languages and then lower coverage in other languages. That's very true. But it's also true that over time, BabbleNet increases coverage and quality. So if I can link at the semantic level, then when later I have new lexicalizations in BabbleNet, I can enable, without doing anything else than releasing a new version of BabbleNet, I can enable all the other tasks that exploit resources linked to BabbleNet. So that's why we chose WordNet. And so what we did was to take all the synsets in the verbal synsets in WordNet, and we're talking about more than 13,000 synsets, and we aggregated them into frames. So we clustered manually. This was quite a hard work with clear guidelines. We clustered these verbal synsets into frames based on similar scenes and similar participants. But these participants, in contrast to VerbNet, were semantic. So there needed to be a semantic participation of similar roles within a certain scenario. And as a result, we created a frame. So we aggregated synsets and we gave a name to this frame. Like, for example, this is the eat byte frame. We created more than 400 of these frames, covering all the 13,000 verbal synsets in WordNet. And so you have the cooking frame, you have the eating byte frame, and so on. Then we also had to take a decision on what to do with semantic roles. As I said, PropBank has the issue that these roles are not readable. Like you have arg0, arg1, arg2. What does it mean? Yeah, we have the proto, agent, and patient, arg0 and arg1, but it's not always the case. And for the other numbers, we don't know exactly what these other means. and it depends on the predicate. So we decided to use instead the inventory of roles from VerbNet, which is this one, which is very readable, with some exceptions. And also we found that some of these semantic roles are quite specific. So we removed some of them, and we obtained 25 semantic roles by re-aggregating some of these grade roles together with other roles that were more general among the ones selected. So as a result, we could have a small inventory of semantic roles. And for each frame, we manually identified, based on the examples in the WordNet definitions and based on the semantics of these scene sets, the roles that are normally used in a given frame. So for example, the agent, patient, location frames for eating, the agent, patient, instrument, and result for cooking, because you use a tool and you have a result when you cook. And so some statistics show you that this new resource that is called Verb Atlas, and that is available online and downloadable, and also queryable online, as I'll show you in a second, cover the full set of verbal meanings from WordNet. While, as you can see, for example, VerbNet has lower coverage of sentences. In FrameNet, you have 5,000 frames. PropBank has quite high coverage of meaning units, but not covering the whole lexicon. In terms of frames, we have a low number of frames, which is good because you can manage coarse frames like eating, like cooking, and so on. Less than 500. And as I said, 25 semantic roles. Also, and this addresses all the issues that I mentioned. And again, I want to highlight, these are fantastic resources, but resources are created at a certain time when some other things are not needed. Like, I don't know, multilinguality was not a key point when many of these resources were created. While we created Verb Atlas last year and we're still improving it. And so this is what makes it appealing to the needs of today's research. Also, as I said, we were very careful at linking to WordNet and as a result to BubbleNet. And also, importantly, we linked to PropBank. So each scene set each scene set is linked to a predicate in PropBank, so that as a result, you can exploit PropBank annotated data, which is used for semantic role labeling, and also exploit the Verb Atlas frame annotations that result from this mapping from PropBank. So what we did was just to add the frame information. So because, as I said, the training data is tagged with PropBank, we can also view it as tagged with Verb Atlas, thanks to the mapping. So we also added a component which not only performs predicate disambiguation with PropBank, but also performs frame disambiguation with Verb Atlas. So it tries to disambiguate the verb with the right frame from Verb Atlas, which is quite coarse-grained and takes advantage of the fact that different verbs that fall into the same class can benefit from this information, because I'll end up disambiguating with the same frame in Verb Atlas, while I end up disambiguating with a different PropBank predicate here. And then we also train the PropBank role scorer together with the Verb Atlas role scorer, which is cross-frame, because an agent is an agent, while an arg0, arg2 in PropBank depends on the predicate. So here we have cross-frame and cross-predicate information. And so we train together. And what we achieve is a considerable improvement in performance. So if we take the baseline, which is the system that uses PropBank to train on the Cornell 2009 dataset for semantic role labeling on English here, we achieve, if we look at the F1 score, we achieve an improvement in F1 score, which is not that big, within the in-domain evaluation, but still statistically significant, because this is a quite large test set. And so this means that using verbatas and PropBank is better than just using PropBank. Then if we test on the out-of-domain evaluation, where the test set is from a different domain than the training data set, here we see a considerable improvement in performance. This is a 0.7 improvement, which means that using verbatless information helps generalize across domains. And so this is, I think, an interesting result. We're also comparing with other high-performance systems, and as you can see, using verbatless helps. And we found this also in other experiments in submitted papers, but that I cannot mention here. Finally, we also checked what happens when this is for role labeling. So these results that I showed are for role labeling. While for predicate disambiguation, so if I have to choose the right meaning of the predicate, what happens? Well, again, here you can see that our baseline gets 95% performance in predicate disambiguation, while using verbatless helps improve by 1 point over Tsai and by 0.5 over He et al., which is another competitive system. And so this is outperforming the pre-BERT state-of-the-art in predicate disambiguation. If we use BERT, there are slightly better systems, but using verbatas further improves them too. And so before the conclusions, I wanted to show verbatless. So you just go to verbatas.org or just type verbatas on Google, and you can download it. You can use an API. You can query it. And these are the frames, for example, for eating. And if I go to eat bite, for example, these are the scene sets that concern that are clustered into the eat byte frame, and you can see these are all the scene sets from WordNet that have to do with eating or biting. And you have also a link to BabbleNet so that you can realize, even though this interface is only for English, but you can realize that in a few months we could potentially have a button here that shows the information in another language thanks to BabbleNet, thanks to going to the corresponding scene set, multilingual scene set in BabbleNet. And here you see the frame-specific roles. And also, one thing that I didn't mention is that we manually provided selection of preferences that are from a small semantic taxonomy that could be used for improving for later determining whether the roles are correctly classified. And there's also a system integrated with this interface. So if you say, I don't know, the mouse ate the cheese that I bought at the supermarket, this will understand it's a sentence and will use our semantic role labeling system to tag it with verbatless. And so you see this is the eat byte frame, this is the agent, this is the patient, the whole clause is the patient, and both is in the bind frame, and the agent is I, and what I bought is the theme. And you can also view the same annotation thanks to the mapping to PropBank. So I think this is what we wanted, and this is very cool. And I look forward to moving to any other language thanks to BabbleNet. I saw a question, but let me finish and then I'll answer the question. So in conclusion, natural language understanding is true that the recent developments in transformer-based architectures considerably improved natural language understanding, in my opinion, and also in many tasks. However, I strongly believe in the integration of these deep learning approaches with symbolic and knowledge-based approaches that can exploit the structure that is available in a general purpose resource that is independent of the task in which we are performing NLU. And normally, it's easy to see that these transformer-based architectures or in general deep learning performs very well on English, but it's harder to see this improvement across languages. We showed that this lack of knowledge and lack of annotated data can be relieved by using multilingual information from knowledge resources. And so we relieve the knowledge acquisition bottleneck by showing that this information can take WSD and semantic role labeling beyond the current state of the art, which is standard supervised approaches, and make the systems, and in my opinion, as important as beating the state of the art is also showing that these systems and their outputs are more understandable, more readable and scalable for humans, so that I can read the output and give an explanation to the output, and maybe later correct these annotations, because I can read them and I can say, no, it's not this meaning, it's this other meaning, so I can inform the system later. And as I said, all the approaches can scale across languages thanks to BabbleNet. So thanks a lot, and the best word I could find that includes the ERC, which funded this research, is merci. And I thank you all, and now I'm ready to answer the questions. And
First of all, thank you very much, Roberto, for this impressive talk covering a lot of ground. I'm glad we have the Q&A session scheduled at 11, where there'll be more opportunity. I'm sure there's more questions to you. There is one in the Q&A. I think one has been resolved.
One has been answered. So there's an API. You can go online to Verbatlas and check it out. It's an online API, but you can also download the data, the whole set of data, and use it. And we're also building an offline API for use, but that will be available later, probably after the summer. The online API is available. You can download the data.
Perfect. Sorry. So perhaps let's take the question by Matthias Müller.
Machine translation is often used as an anecdotal example to motivate WSD. I'm aware of work, and I guess you are also aware, but not so recent. There is some recent work, but I agree that that this link between WSD and MMT, which is quite historical, because WSD was found to be a relevant task as soon as MT translation was found to be an issue right after the Second World War. And we have some work, but still preliminary, and I understand it's very difficult to show that WSD would really improve MT, especially if you don't achieve very high performance. And so now that, so if you consider that in the past 15 years, we have moved from 65% to 80% in fine-grained disambiguation, I think if we do something to further make this semantics coarser, or exploit together the fine-grained semantics that is found and the coarser grained, I think we can achieve this. But I'm not aware of current work that shows this improvement. So this is ongoing work, and I think we will all try to do that. As we now have good systems, did you think about exploiting humans and machines more closely to produce more validated data? Yes, absolutely. Compared to purely human or purely machine-based data, yeah. So we have been working on the semi-automatic creation of data. Well, actually, fully automatic, but from partially manually annotated data. We have a whole research direction called Train-O-Matic that you can find out. But I understand what you're saying. So you're saying, can we involve both humans directly in the annotation, maybe like active learning or some other approach that exploits the output of high performance systems to further improve and further produce more data? And this is what we are doing, because in creating this data for the seminal tasks, that's exactly what we are doing. So we are trying to produce a lot of high quality data, starting from automatic annotations and then asking humans to validate them. But I think there's a lot of interesting stuff to be done here. We also did some work on gamification, video games with a purpose, but there's a lot that could be done. Yes, I agree that now that you have 80% in WSD, in at least a number of languages, I think you can do a lot.
Perfect. Thank you very much, Roberto. The session